of our caps. Let's summarize what we did with the capacitor. So we want to do a summary.
No, it's just a hangout.
of
Lecture everybody. I'm down.
Okay, so what I'm assuming here is that effectively, when I write down a capacitor circuit, I imagine that I have some switch. And then we have a capacitor. We have some voltage. And one of the things that we said here is that when we throw this switch at t equals to 0, what we find here is that initially, so before switch is thrown, and in this case it's thrown closed here, we're going to say that the voltage of the capacitor, look at my minus sign. Minus sign says that what was the charge, what was the voltage of the capacitor just before I threw the switch? We're going to say it's 0. So that means that I have an uncharged capacitor. What this tells me here is that at t equals to 0 plus, now we have a charging process. And when we have a charging process, what we said here is that if the voltage across the source is not equal to the voltage of the capacitor, then there's a current flow. And we talked about current flow already. So when I look at current flow, that tells me that at 0 plus, this is not equal to 0. That means there is current flow. Now what you find here is that we could imagine that the wires here represent some non-zero resistance. And what we did here is that we started to look at the plot of the capacitor here. And what we're seeing here is that if this is the place where the capacitor gets fully charged, we see the standard sort of like RC behavior that you were taught. And when you look at this curve, what does this thing mean here? Well, the voltage changes as a function of time now. And what we're seeing here is that if I use the capacitor equation, which says that the charge is equal to the voltage times the capacitance of the element here, it said if I take the derivative of this guy, this tells me here that the slope of VC versus T is the current. So if I look at the current here, what I'm really finding here is that the slope of the current, of the voltage here, that represents IC. And what you're seeing here, that if I look at that slope in the initial stages, the current changes very, very, very quickly. And if it changes very quickly, then the capacitor charges up very quickly. As time goes on, the current, you can see, has a lower slope here, so therefore it's charging at a slower rate here. And at some point here, we could say that at t equals to infinity, then we say that we have a fully charged cap. So in this scenario here, we said that there is no current flow. So if I have a fully charged capacitor, then that means that the drop between the capacitor and the source is 0. There's no difference between these two. I get no current flow. No current flow means that the current of the capacitor is now 0 here. That's what we mean by a fully charged capacitor. So one of the things that we should do here is that what you're finding here is that capacitors voltage cannot change instantaneously. So when you look at this curve tells us that initially there is a very quick charge, but what you'll find here is that I can't instantly go up to the voltage of the source here. You know, there was a paper where they were talking about, in the Sentinel, if I remember correctly, where they were talking about charging of electric cars. And they were saying that they could get an instantaneous charge. What do you think they mean by instantaneous charge in this case? That I would have what? A very small RC time. That it would look like it's almost charging instantaneously. But we know that that can't be true. Because if we did, then that would mean what? Well, what would happen? So if I could change, so if one could change voltage instantaneously, what does this mean? Well, if I look at this guy here, look at this guy. If I can change that, then that means that dV dt, that means that the slope would have to be what? Effectively infinite. So that means here that the slope must be infinite. And so therefore that tells me that the current IC is very large. And in some of these situations, you could get what they call dielectric breakdowns. Right? So if I don't know if you've ever taken a CAT. I was telling my 4B students over the summer here that I had a group of electrical engineers, I don't know, maybe about 15, 18 years ago. They used to mine the capacitors out of TV. And then what they did here is that they put them all in parallel and they charged them up. So they were taking the power supply, and then all of a sudden what they would do here is that they would discharge the capacitors on slinkies. And you could actually see them arc weld the slinkies together. Well, first of all, you shouldn't be doing it on my time, right? Because that's absolutely dangerous. So they had, I think, like 5 capacitors at 40 volts, and the amount of current that they could produce is significant. So as soon as I saw that, of course, you just picked up the power supplies and didn't let them do that, right? Because if you do something very silly, I mean, who knows what could happen, right? There's some people that can take it. I have a friend, God, this guy is kind of insane as far as I'm concerned. He can take the leads, you know, of outlet wires, which is 120, and he just, yeah, that's about 120. Then he would, he'd get the zap, and apparently it didn't bother him. All I know is that every time I've gotten bit by those lines, it hurt. But this guy seemed to kind of enjoy it. I guess if you enjoy a root canal, that might be fun. But as far as we're concerned, that's not the case. So you really can't change the voltage of the capacitor very quickly. By the way, if the current is very large, then what you really do here is that you get dielectric breakdown. Of the insulator of the capacitor. Now, I don't want to go too much time into this here, most capacitors already leak, but if you dielectric break down even more so across these, then you'll get a leak, and then you'll see that the capacitor is effectively dead. You can't really use it. Or the leak is so high that it doesn't exist. It's like a short in some sense. So what we could say here is that there's one thing that we can say here. So if I look at the voltage of the capacitor before, the voltage of the capacitor afterwards, and what we say here is that the voltage cannot change instantaneously. However, the current of the capacitor does not have to equal the current before and after a switch being thrown. So in this case here, we say that the current can change instantaneously. And sort of like, this is like super, super important in this chapter right here. It's a big deal. These are the things that we will carry with us. And you'll see when we start to do mathematical calculations, I mean, you'll see. And what we'll mean by this here is that you could look at a lot of times, well, so if you look at the voltage of the capacitor, what's it going to look like? Like that. So it's going to look like this, and what you're going to see here is that there is no discontinuities. Okay, there's no discontinuities. But if I plot the current of the capacitor, and what you'll find, so I should be careful here. So if I'm talking about an uncharged capacitor, it looks like this. So if I look at this, even when the switch is thrown, you get this behavior where they're connected. That is not true of the current of a capacitor. And typically what you look at is you don't look at the capacitor, you typically look at a resistor that will be in series with the circuit when you look at that. Or if you have another resistor that you're looking at, you're now looking at the current of some other resistor where this is part of that thing. And what you could find here is that the current could be coming like this and then instantly could jump like that. So what you're seeing here is that you see discontinuities. Okay, you see discontinuities in the current. So it can change. And another thing that you'll see here is that the current is very, very sensitive to a change because it's the slope. So here, if I go from here to here, what you'll find here is that the slope can change quite a bit depending on how you're looking at this. So just to sort of like help you with the problem set, what we want to look at here is that we could sort of like talk about how does the voltage change across a cap. And the way we answer that is that we come in and we start looking at this guy right here. So if I'm looking at how is the voltage changing in a capacitor, what you'll see here is that I start off with this guy right here, which means that that's just a first order equation. We can integrate that guy, and if we integrate this guy, you can see here that I could write this as dc of t. And then I'm assuming that before the switch is thrown, I'll put a 0 here. This tells me what the initial voltage was. And in this case here, so if I look at the example that we were talking, the initial voltage here, you can see here, in this case, at 0 minus is 0. And then the charging starts here. So now the only way I can change the voltage across the capacitor is if I just integrate the current as a function of time here. And I'm assuming I'm going to go from some initial value to some final value. And so if I look at this guy here, this essentially tells me it's the voltage accumulated. I think that's right. That looks really wrong. Okay, let's try one more time. Accumulated. You know what? I really don't care. Between so this is what we're having right here. Right, it's the voltage accumulated for that current between that time and that time. If I have a constant current, then I'm going to get what? A constant flow of charge. And therefore, the voltage should increase, linearly as we do that. So, that being said, let's go to the first example. You guys ever hear of Franklin panes? They were developed by Benjamin Franklin. He thought that, so that's when, if I remember correctly, they're sort of like the analog of a Leyden jar. I assume you know what a Leyden jar is. And when you look at these Leyden jars, it's just a big ass capacitor. And I hear that they can get up to the order of a farad or something, which is an enormous amount of capacity. So he developed these panes, and he thought that he could use these to essentially, instead of beheading the turkey, you would just zap them and kill them. But apparently, he shorted them out. And he has this wonderful quote, something like, maybe it was a goose that he was trying to, I can't remember, but it's something like to the order of like, instead of, shocking this, this turkey, I almost cooked my goose. He was the goose. He actually knocked them out. It totally, because these Leyden jars are massive for capacitors here. So let's look at this first example. That's what I said, these capacitors from these old TVs. Some of these capacitors, I've heard of people getting seriously injured mining capacitors out of TVs because they don't discharge. So like if you were to do that after this lecture, one of the things that you want to make sure here, by the way, these are the old tube TVs. Not the ones, I don't know if they had, I don't know how they're run actually, so I can't really say. But you would have to discharge them to be careful. So what you have here is that you have this circuit right here. And here's the source. And I got a nice circuit here. And you can see this is a 2 ohm. This is a 0.1 farad capacitor. And we're looking at the voltage of the capacitor. And what you're finding here is that they're telling you that the initial voltage of the capacitor is minus 4 volts. Okay? So if I look at what the current source is, the current source is a function of time. And what you're seeing here is that it goes up linearly and then it flattens out. And then turns off here. And what you're seeing here is that this guy is of the order of 2 amps. This is at 0.25 seconds, and this is at 0.5 seconds. Well, we're plotting time here. So what our goal here is to find out, what we want to do here is that we want to determine VC of t for t greater than or equal to 0. So physically, I want you to think about this circuit. What is happening? What the hell does that mean, by the way? Now, if I have a charged capacitor, what this is telling me here is that I have a capacitor that has what? It has a drop of 4 volts across this thing. So now what's going to happen here is that I'm going to take this capacitor and I'm going to have, in theory here, I have to have a switch. Okay? So if I take this capacitor, if this is the case here, I'm going to take it into the circuit. What am I going to do? I'm going to flip it. And I'm going to put it in there. But because this is open, there can't be any current flow. Or if there's any current flow, it happens very, very fast until it stops. And then what do? I close it. So what is this current doing to the capacitor? Well, if it's negatively charged at this end, I have the flow of positive charge. So to build up voltage on this capacitor, what I got to do here is I got to do what? I essentially got to change the polarity of this capacitor. And after I change the polarity of this capacitor, at some point, maybe I'm going to go above negative 4 volts. I don't know. We'll calculate that. But physically, that's what has to happen. Right? I can't just put in a capacitor with the circuit like that. I have to have some switch. Then I put it in, and then I close it. And if you've done the capacitor labs here at Cabrillo, you know that this voltage of these capacitors, you got to be very, very, very careful. We have these really high resistance. You can't put a meter will discharge it. So there you have to have meters that have orders of very high, I think the ones that we have, what are they? I think they're about 100 giga-ohms. So the resistance is so high that you can't leak charge off of this capacitor. So what you find then is that now the switch closed, and then that happens. So if I want to look at the charge buildup here, so for the charge slash voltage buildup, we use that equation right there. And what you're seeing here is that because of the way this thing is, I know that initially the charge here of the capacitor has to be what? Negative 4 volts. So it's below the line. So if I'm looking at this guy here, I have what? I have the initial charge plus the capacitance in this case is what? 0.01 farad. And then I'm going to integrate this guy for I source of t dt here. So if this is minus 4 volts, then I'm going to have to break up this integral into what? 2 different regions, because there's a discontinuity as far as the integration is concerned here. So when I'm looking at this thing here, what if we plot VC versus T? What you're seeing here is that if I'm looking at this guy here, where am I starting at? I'm starting at right there, which will be minus 4 volts. So if I start to add positive charge to this thing here, then that means then I'm going to get my flow of whatever else I'm going to do with that here. So now we see that we have 2 intervals. So if I look at the first interval here, I'm going to be looking at between 0 and 0.25 seconds as my first interval. So let's look at this first interval right here. So the first thing that we see for this first interval here, I got to go in and I got to get what? I got to parameterize this curve. What's the slope of this curve? Well, it's got to be 2 divided by a quarter, so that's got to give me a slope of 8. And note that the intercept must be 0. So right away, so if I look at the current of this guy here, it's got to be 8t plus 0 for the slope. For the intercept, excuse me. So then if I come in and I integrate this guy, note that I'm going to get positive charge. So the voltage has to then what? Increase. I'm going from a negative number and I'm going to have positive flow. So therefore, I should be approaching 0 in this case. So if I look at this guy here, so then if I integrate between these guys here, I'm going to start off at -4 plus 10, the integral from 0 to 0.25 of 8t dt. So if I start to integrate this guy, what we're seeing here is I should get a value of what? Well, I'm going to get -4, I got 80, and then I'm going to get t squared over 2. The only term that matters is this quarter here, so then I'm going to get between 0 to 5 seconds here, and if you compute this number, you're going to see that I'm going to get what? I'm going to get that as VC is 0 minus, I get -4. Now at a quarter, I'm just going to start to do this for a quarter. You're going to see that I'm going to get VC at 0.25. I'm going to get a number, if I plug it in, as -1.5 volts. Right? So you're seeing that I started at -4. I'm increasing in voltage. And if I was to put an intermediate value here, just to remind you here, I did this for 1/8 of a second. I ended up getting -3.38 volts. So what you're seeing here is that the voltage is going from a negative number to a more positive number, even though it's more negative. Right? So this is the function that actually gives me that. So now if I look at the second interval is now between 0.25 t and it goes to what? 6.5 here. Actually, 0.5. So if I look at this guy here, then I'm going to start from what? So if I start from C at 0t less than 0.5, then this really means what? I get the voltage of the cap between 0t and 2.25 plus the voltage of the capacitor between 0.25 and 0.5. So if I look at what do I have all the way up from here to there, what I'm going to see then is that up to this point here, you can see that I got to have -1.5 volts. And so the remainder part of this guy here has to be where I'm going to do what? I'm going to integrate this constant term. And this constant term you can see is 2 amps here. So then I'm going to go 2 dt here. And if I integrate this guy, what am I actually seeing here? I'm getting -1.5 V plus I got 2 times 10, which is 20. So then I should get 20 of t, where now I'm looking at these intervals right here. So my function is definitely this guy right here. So if I integrate this, so what you can see here is that if I set t equal to 0, I still get the same value that I would get right here. But you can see that if I integrate from here to here, and I look at this number, what you end up seeing here is that you're going to get minus